Autoencoders are a specific set of deep neural networks used to extract latent features from a specific representation of data. So in this figure, what you see is like PCA, principal component analysis, is trying to understand the data. So it clusters the data into this specific set of groups that it identifies from the existing data. So each principal component it understood is shown with different colors. So if you take a look at the output from the linear autoencoder, it has the similar representation, but the only difference is it has been rotated in a different angle. So this brown patch, it's here. So but if you take a look at this shape, it has the same shape here. So autoencoders are one way of understanding a specific representation in a specific dataset. So autoencoders can be used to reconstruct things. So for instance, you take a look at set of original images like this. So this is the MNIST fashion dataset, and you use a autoencoder to reconstruct a similar one. So you can see there's a similarity, and you use a PCA to do the same reconstruction. So you try to create a similar object like this, but you can see autoencoder is obviously doing better than a PCA in certain times. This depends on the way you train, the way you define the model. Autoencoder consists of two parts. So in the previous defining section, I explained what is an autoencoder. So autoencoder has two parts, an encoder and a decoder. The encoder, what it does is it tries to understand the data, understand the data distribution, and create a low dimensional format after understanding that. So this becomes a tensor basically. So it's a low dimensional understanding of the input data. So starting from here, the output layer tries to interpret these identified features and again form the expected output, which is x dash. So you input x and you create this h tensor, and you get the expected output x dash from the decoder. So basically, when it comes to a simple format of a variational autoencoder, this is basically known as a vanilla format. So it's the basic building block of autoencoder. So in autoencoder, what happens is like the encoder tries to identify the latent features, hidden parameters, hidden information from the input data. For instance, if it's a denoising application, it tries to understand the original features from the original signal, and in the decoding phase it's trying to do a denoising if it's an audio denoising problem. If it's a signal denoising problem of an image, it's going to reduce noise as much as possible. So the decoder tries to approximate the original input as much as possible. So in these cases, a metric like mean squared error can be used to evaluate the trained model, how good it is working. When it comes to using autoencoders, there are some set of matrices used by different set of applications. Let's take a look at a image denoising problem. So if you denoise an image and create a better output from a noise image, you need to evaluate the output image and the expected output. For this case, you can use a index like a structural similarity index. So this is one of the famous and mostly used index to evaluate output created in forms of an image. And also you can use SNR in image as well. But SNR is highly used with the audio signals because that's one of the basic things when it comes to do a denoising on an audio signal. So you have a clean signal and it's being noised by some other set of voices or other set of other noises. So you evaluate the denoised signal along with the noise. So that ratio gives you an evaluation how good this denoising is. So these are the two metrics used in evaluating an autoencoder. So this is some example where signal denoising is done. So you have a speech and you have a noise included there. So DNN tries to understand what's going on here, and it's trying to remove the noise from there and create the original signal. So this is one of the mostly understood application with autoencoders, removing noise from audio signal. So it can be done by a simple deep neural network. So you can again use a couple of dense layers followed by some activation layers. Then you can create a denoised signal once you train the model. So this is a very primary set of applications developed with autoencoders. In addition to signal denoising and image restoration, autoencoders has also been used for anomaly detection. So in an anomaly detection, what you basically do is like you pre-process a signal and you have to define whether this specific output coming from a specific engine or a specific source is an anomaly or not. So you definitely have to define the threshold. So the idea of the autoencoder is to define this threshold so that it's really good, so it can understand an actual anomaly and non-anomaly condition. So that's the basic idea. Autoencoders are also used for image recognition. So in an image recognition problem, when you insert the input as set of images, it tries to extract different set of features. So that's why we put different hidden layers. So from each hidden layer, specific parameter is being understood. From this input layer, it tries to recognize the patterns of the local contrast, so how the contrast distribution is. And in the hidden layer, it tries to understand certain features in the face. So you have eyes, nose, a mouth, and other features. So it tries to understand these features from there. In the another layer, the characteristics regarding the face, the overall face, is being identified. So likewise, an autoencoder can be used for image recognition as well.